All right, continuing where we left off again in this third video. So the recording for the three trials, how's that going to look like? Okay, so the mass of the empty calorimeter on all three experiments is 18.6 grams. The initial temperature of the calorimeter is room temperature, so it's 21.5 in all three trials. Okay. In the first trial, to calculate the moles of magnesium, you have to take the grams of magnesium divided by what it's called is molar mass. All right. So if you look up molar mass in the periodic table for magnesium, it's around 24. So 24.305 grams per mole to be exact, right? So if you take the given mass divided by molar mass, you get moles. All right, that's how it works out. So for the first trial, you are working with 0.00617 mole of magnesium. Okay. The maximum temperature that was reached after the reaction of the magnesium and the hydrochloric acid for trial 1 was 30.7. So from 21.5, the temperature rose to 30.7 after the reaction. Okay. So the mass of the calorimeter plus the reaction contents after the reaction was over was 68.97. Okay, so the initial calorimeter mass empty was 18.6. The final mass was 68.7. If you take the change in the mass, you will get the mass of the content itself. You're removing the mass of the empty calorimeter, and so the mass of the content itself, that is the water, the hydrochloric acid and the magnesium, is 50.37 grams. The change in temperature is the 30.7 minus the 21.5, and that comes out to be 9.2 degrees centigrade. So in the second trial, again, you take the grams that was weighed out divided by the molar mass. Again, you get 0.0103 mole of magnesium. Maximum temperature reached in the second experiment was 36.9. Mass of the calorimeter and the contents 69.06. So 69.06 minus the empty calorimeter mass, 50.46 is the mass of the contents of the calorimeter. The change in temperature, 36.9 minus the initial temperature, so 15.4 degrees centigrade. So recording for the three trials, all right, 0.35 divided by the 24.305 for the third trial, 0.0144 mole of magnesium. T final 42.9. Mass of the calorimeter and contents after the reaction 69.15. Okay, so 69.15 minus the 18.67, 50.53. The change in temperature 21.4. Okay. All right, so you have a dizzying array of numbers, and we have to put it all together. All right. So we have the first experiment, which was taking the Ccal measurements, which I believe was about 10 joules per degree centigrade, times the change in temperature, and then the heat from the average heat from each of the trials. That will give us the total heat for this reaction. So the Q trial or the Q reaction is mass times the specific heat of water times the change in temperature, all right? And then we have to average them out. The Ccal, which we calculated from experiment 1, was 10 joules per degree centigrade. So for trial 1, the delta T was 9.2. For trial 2, the delta T was 15.4. And for trial 3, the delta T was 21.4. So Q trial 1 is the mass of the contents times the 4.184 times the delta T. So that is 50.37 times the 4.184 times the 9.2, and that comes out to be 1938 joules. For the second trial, it was 50.46 times 4.184 times 15.4, and that comes out to be 3251 joules. And then for the third trial, 50.53 times 4.184 times the 21.4, and that's 4524 joules, all right? So in trial 1, you're going to take the Ccal times the delta T plus the Q from trial 1, all right? That would be the total heat of that reaction for trial 1. So 10, which is the Ccal, 10 joules per degree centigrade. The delta T for trial 1 was 9.2. And if you go back, you will see that trial 1 was 1938 joules, all right? The Q for trial 1 was 1938. So you plug that in here, and when you do the math, you get 2030 joules, all right? So if you divide this by 1,000, move the decimal point 1, 2, and 3 places, you convert it into kilojoules, which is 2.030 kilojoules. You do the same thing for trials 2 and 3 with their respective numbers. So again, Ccal times the delta T for trial 2, 15.4, plus that Q for trial 2, which was 3251, and then you get 3405 joules. Convert it into kilojoules, and it's 3.405 kilojoules. Again, do the same thing for trial 3. So you get 10 times 21.4, 4524, and the number comes out to be 4738 joules, or 4.738 kilojoules. So now you have the kilojoules for each of the trials: 2.03 for the first, 3.4, 1 for the second, and 4.74 for the third. Now you're going to take that heat and find the molar heat. That means you'll take the kilojoules and then divide it by the moles that we had calculated previously for each of the trials, okay? So the molar heat is going to be the Q, or the heat of each of the trials, divided by the moles of magnesium used in that trial, okay? So for the first one, it's 2.03 kilojoules divided by 0.00617 moles, and that comes out to be 329 kilojoules per mole of magnesium. The second trial, 3.405 divided by the 0.0103, and it comes out to be 331 kilojoules per mole. And then the this is a typo here. This is trial 2, this is trial 3. So trial 1, trial 2, and trial 3. And so trial 3 is 4.738 divided by the 0.0144, and it comes out to be 329 kilojoules. So you can see that there is reproducibility, because in each reaction, if you look at the kilojoules per mole, it's so close, all right? Again, the molar heat of a reaction is again an intrinsic property. It doesn't change. You can have different heats and different moles, but in the end, per mole of that reactant, it's a constant value. So then you add up those molar heat of reactions from all the 3 trials divided by 3 and take the average, which comes out to be around 330 kilojoules per mole. Okay, so this is the average molar heat of reaction for the reaction of magnesium and hydrochloric acid. All right. And now you go on to completing your lab report once you have all your data in place. Okay, so the aim of the first part of the experiment is to determine the calorimeter constant. The second part of the experiment was to determine the molar heat for the reaction of magnesium, metal, and the hydrochloric acid by doing those 3 trials and then averaging out that molar heat of reaction. In the first one, I predicted that the heat transfer to the walls of the calorimeter would be a small number compared to the heat that is transferred to the solution inside the calorimeter, right? And in experiment 2, I predicted that the heat from the reaction would be pretty high from this reaction. And so with each trial, the heat transferred would also increase. At least that was my hypothesis, although the results proved that it's about the same because you're doing pretty much the same reaction in each case. All right. And so again, like the molar heat, which we discovered, is a very intrinsic property of a reaction. So this part you would know how to do all that, so I won't go through it. You know how to list all the materials, equipment used, etc. Write down your procedure, and then write down all your results, what you got after writing down all your data. All right, so make sure that you list all your data. Again, sometimes it's tedious and it seems redundant, but again, it's a good habit to keep practicing writing down the data and then in the results explain. So now coming to the conclusions part, what did you learn from these experiments? All right. So one of the things is, how do you actually measure and calculate heat when you're doing a reaction? Because heat is something that has to be calculated indirectly. You can't just have an instrument that directly calculates heat. That is not possible. So using an indirect method of calculating the heat through using a thermometer, for instance, all right? So you're monitoring the temperature of that solution in a closed container, and the closed container is important because it's an insulator, so it'll keep all the heat contained inside the container, all right? So the calorimeter is a good way to do this kind of experiments where you're making an indirect heat measurement. All right, so it gives us a method where you can measure that heat transfer, and it doesn't have to be always a chemical reaction. For example, the bomb calorimeter was used to determine the calorie content of different items, foods, etc. All right, so suppose, what would be the purpose for learning calorimeter as a nurse? Suppose you want to find the calories of a certain food and you are unsure if it was the right choice of food for your patients. What do you do? Find yourself a calorimeter and burn that food? On the other hand, you could look up the calorie content using readily available charts on the internet, for example. All right. So real world example of the use of calorimeters mainly by food companies who use it to determine the calorie contents of food and sometimes even the non-food items. All right, so if you look at the food packages, cereal boxes, etc., this is how they have determined the calorie contents of various foods